Let me show you a mathematical magic trick. Consider some sequence of numbers a sub n. So a sequence of numbers could be 0, 2, 4, 6, 8, 10, 12, 14, and so on, right? The even positive numbers. Then the generating function for that sequence of numbers is given by the power series where the coefficient of x to the n is the nth element of your sequence a sub n. So for instance, the generating function of the even positive integers would look like this: 2x plus 4x squared plus 6x cubed plus 8x to the 4, and so on and so on. Now to show you this magic trick, we're going to consider some recursively defined sequence of numbers. For this example, consider a sequence where its 0th term is 5, and then for every subsequent term a sub n plus 1, it'll be given by 3 plus 2 times the previous term a sub n. So we can use this rule and fill in the little table I have here to find the first couple elements of this sequence. As we said, the 0th element will be 5, and then the first element will be 3 plus 2 times 5, which is 13. Then the next element will be 3 plus 2 times 13, which is 29. And then next would be 61, 125, and 253, and so on. Now what I want to do is find the generating function for the sequence a sub n. So what we'll do is say that g of x is equal to this power series where the coefficients are a sub n, our sequence. So the first thing I'll do here is I'll split off the a sub 0 term because I already know that a sub 0 is 5. So I'll have 5 plus the rest of this sum. And now what I'll do is I'll re-index the sum such that it starts from 0 and we'll be doing it over a n plus 1 x to the n plus 1. And now I can use the definition of a sub n plus 1 being 3 plus 2 times a sub n. So I'll resubstitute that here. Now once we split this sum over the sums, we'll recognize that x to the n plus 1 can have an x factored outside, giving us 5 plus 3x times the sum over positive integers n of x to the n, plus 2x times what we recognize just to be our generating function. Recognizing this sum over x to the n to be a geometric series, we can rewrite our generating function in terms of itself and, rational polynomials. We can then use a little bit of algebra to solve for g of x, the generating function. But why would I care at all about this generating function? Well, we need to look at its power series. First, let's do a partial fraction decomposition, and then we'll get a form of g of x, which is easy to expand in a power series. And once we expand everything and get everything into the typical power series form, where we have a sub n times x to the n, we see that we've generated this exact closed form of a sub n. As you can see, 8 times 2 to the n minus 3 generates the same exact sequence as we did using the recursive definition. And so that's some pretty cool stuff. In the next time, I'll show you how we can use the generating function to recover Binet's formula for the nth Fibonacci number. But that's all for now. Thanks so much for watching, and I hope you have a nice day.